okay? Because we're talking about rupture forces and interactions between two biomolecules, okay? Now, what they found is that so they did this experiment, AFM, and then instead of this dependence, exponential dependence of lifetime as a function of force, they found that lifetime first increases with force and then decreases with force. Okay? And that is directly related to the shear threshold effect, that you had this biphasic kind of dependence. Now you have, again, biphasic kind of dependence, but now for the lifetime. Why? Because now you're working at the level of single molecules. Okay? So same biphasic dependence, same strange behavior, and so they call this regime catch. You know, the stronger you pull, the stronger bond becomes, so it catches, holds on to the ligand, kind of, okay? And then once you reach certain threshold, and it's around 10, 15 piconewtons or so, then you are immediately into the sleep regime, and that's when you have intuitive exponential dependence of the lifetime as a function of force. So they did it for the monomeric form, for the dimeric form of PHGL1, and then they also did it for this molecule, you know, monoclonal antibody, just to compare. So for monoclonal antibody, you have just a sleep dependence. You know, the dependence that you would expect from Kramers-Smoluchowski theory. But for specific ligands, you have counterintuitive behavior, namely that you have increase and then decrease. Okay? So now, let me briefly say a few words about the biological importance of this. Well, every single time you see a rolling leukocyte, so this is a rolling leukocyte, and you have some ligands expressed on the surface, so these are PHGL1 ligands, and then your cardiovascular surface is this one, and you have receptors, PHGL1 receptors. What happens is that every single time you look at this, it has two edges. One is the leading edge, and the other one is trailing edge. So like a bicycle wheel, it has two edges. The leading edge, the one that is advent on the surface, and then the trailing edge, the second one in the back. These two edges. So the slowing down and the prolonged lifetime, like in here, for instance, prolonged lifetime, okay, of the bond allows formation of the ligand receptor complex at the leading edge, okay. So you see. This one, now it has to form here, but this one holds on so that it will not go to the flow. So it will keep rolling on the surface, okay? So if I now translate this conclusion into physical arguments and notions from physics, then the catch-sleep transition couples translational degrees of freedom and rotational rolling motion, okay? What it allows then, what it gives you is that instead of 3D Brownian motion, 3D motion, you know, in the space, in three-dimensional space, you have a almost one-dimensional motion on the surface, which allows you, you know, so the reduction of degrees of freedom allows you to more efficiently search for the site of bacterial infection and tissue injury. So that's the biological relevance, okay? You have a much better now immune system, because it finds tissue injury much faster on performing one-dimensional motion rather than three-dimensional motion, three-dimensional Brownian type of motion. Okay, that's the importance of this phenomena, and this is due to the fact that you have catch-sleep behavior, not just sleep behavior, but dynamic transition between catch and sleep behavior. Okay. So that's what it is. So, and they published it in Nature, and and there were lots of work done on this. And what I have done when I was a postdoc, and we published this paper in Proceedings of National Academy of Science, United States, is that we proposed a simple model for this. So, according to which, we hypothesized that that there are two bound states between P-selectin and PHGL1. One is high affinity bound state LR1, let's call it, and the other one is low affinity bound state LR2, okay? And there are two, there are kinetic rates to go from this state to this one, R12 and R21. And if I'm using Kramers-Smoluchowski theory, then I'll have these expressions for these rates. In addition, I can also unbind from this state with the rate K1, or if I have transitioned into state LR2, then I can unbind from this state with rate K2. Okay? So there is a distance between this minimum and this maximum, and this minimum and this maximum, and that will be x2 minus x1. And then there's a distance from this minimum to this maximum, that's y1, and from this minimum to this maximum, that's y2. Okay? And if I take this slice of this energy surface, then it will look like this, just this curve. So I have two states, one state and second state. This is more stable state, okay? And I have to spend energy F12 to go from more stable state to less stable state. And if I want to go back, then I have to spend energy F21 to go back. So there's a difference F between this energy and this energy. So now, if I don't have force, then I can quickly compute the equilibrium constant, and I can compute the population of this state and this state. So it will be these expressions here. But now if I apply force, what I'm going to do, when I apply force, I will shift the equilibrium. I will change the equilibrium. My force will bend the energy landscape in such a way that less stable state in the absence of force becomes more stable, and more stable state in the absence of force becomes less stable. So in a sense, this minimum will go up and this minimum will go down. What's going to happen is that I'll have a new equilibrium constant that one can compute by evaluating this expression, and new population. So I'll be changing the equilibrium, and I'll be changing the equilibrium population of these two states. Okay? So this is the model, and there's nothing else in that model. And this is a standard model. So this is a Bell model, so-called Bell model. And that's Kramers-Smoluchowski 20, and then sometimes people call it Bell model.